We now are moving to the south of the United States with Professor Mahmoud Reda. Is a distinguished professor and chair of Department of Civil and Construction Environmental Engineering of University of New Mexico. He authored and co-authored more than 350 papers, and he had 10 patents issued and 10 pending in the United States. He is a fellow of the ACI, ASCE, and he's a chair of the ACI committees on nanotechnology. So Professor Mahmoud conducted extensive research on nano-modified and 3D printed concrete and composites for more than 20 years. Professor Mahmoud will give us a lecture today about the 3D printed concrete and composites for resilient concrete infrastructure. So please, Dr. Mahmoud, take the role.
Thank you, Dr. Ahmed, for the introduction. Really appreciate it. I will stop the video for the resolution of the presentation. I'd like to start, of course, by thanking all the speakers. And it's, as Monsef said, it's great to stand on the shoulder of the giants, but it's very difficult to actually make a presentation after the giants. So I hope my presentation will be of interest after these great talks. And I, of course, thank all the organizers for a very nice virtual conference. And I'm very hopeful we all meet in real conferences very soon. So my talk today will be about some of the research we've been doing for the last few years on 3D concrete and composites for resilient concrete structures. So I will talk about give some golden hypothesis about our work, talk about some of the concrete 3D printing and its relation as we see it to infrastructure resilience, and how it ties to large scale 3D printing, talk about the variables for 3D concrete printing, rheology of the concrete and the anisotropy of the 3D printed concrete as well. We'll talk about some, we've been involved in a lot of work on polymer concrete, and so talk about 3D printed polymer concrete and our efforts to try to model and simulate the process and the properties of 3D printed polymer concrete. And then talk about the new experiments and work research we've been doing for the last few years again on pseudoductile 3D printed FRP. Fiber reinforced polymers is coming of big interest in the construction industry. And we're trying to see if we can overcome the challenge of making it ductile. And then we'll talk about the latest research we started recently on cognizant composites. Then we'll wrap up with some conclusions. So the goal basically of a lot of the research we are taking is to engineer 3D printable concrete and composites with significantly improved mechanical properties and capabilities, leading pathways towards smart and resilient infrastructure. So overcoming the challenge of resilience basically by using the new 3D printing technology. And our hypothesis is that if we can use the nanomaterials and the nanotechnology research that we and many of the other researchers you heard about from today have been involved in using nanotechnology in concrete and in polymers, and combine it with 3D printing technology, we can create a new generation of concrete and composites that have superior properties that might have some intelligence and be able to help us in the challenge of resilience. Looking at concrete 3D printing as an emerging technology and tying this to the previous talk Dr. Nehdi gave is interesting because we could see that there is a general, what we call as the hype of innovation, Gartner hype. For a lot of technologies that appear today, and we'll try to locate where is 3D concrete printing in it. So this has been studied by others, and they looked at for many of the technologies. So usually when you have a technology, you start by what we call as a period of innovation trigger. That's when the technology appeared. Then you can come to a peak of inflated expectations where people expected that you are going to do everything with this technology. And then a drop in this was what's known as the trough of disillusionment. And then the slope of enlightenment basically representing the fact that if the technology can survive that drop, then it will actually go back to its use and move to the industry and actually go to the plateau of productivity and being used. So we see 3D printing technology or the autonomy in construction as in that part. So the large scale 3D concrete printing, we could see that it's still very early in the innovation trigger. The lab scale one actually have been happening now for close to little less than a decade. So it is coming up. Now we did not pass this drop yet. So hopefully we have enough in our bucket of this work and technology that can be used for real applications. So when you have this drop, then you can go back and start contributing to the real industrial applications, like, for example, the building information management systems, BIM, or the fiber optic sensing, which is being widely used now in the industry, or what we just talked about, like carbon fibers and composites, that now is a real infrastructure material that many of us use. So the relation to resilience also relate to this concept of performance and performance drop due to the events. So this solid red line here is representing an infrastructure performance with time, where the structure would observe some typical aging and the drop in performance, small one, with time. And then when an extreme event like a hurricane, like an earthquake, like any other extreme event happened because of the climate change we're observing or other man-made reasons, that you will see a major drop in the performance. The robustness of the structural design and the systems design we do today will allow hopefully the system not to completely collapse. And with some of the redundancy we have, you have the system performance here. Now recovery requires some repair or interference. And how fast this recovery can happen is representing how resilient is the structure. So structures that recover very slowly are much, or don't recover at all, are not as resilient. And the structures that actually can recover quickly. We believe the concrete 3D printing can help in improving the recovery and the rapid recovery, or improving the rapidity, which is strongly related to the infrastructure resilience. So an example here, we just for pictorial representation, we show a bridge, for example, that is exposed to disaster, and the post-disaster bridge collapse. And the interference here with concrete 3D printing, we'll talk about a little bit about having concrete printing of post-tension bridges, and the speed that can be happening, and the use of the combination of 3D printing and post-tensioning technology, where we can restore functionality of the structure quickly. This is an example of a 3D printed trapezoidal box girder bridge that we have printed in our lab. This is a concrete that is about 10,000 psi, about 70 megapascal strength. An example of a cross-section of about, this cross-section is about 1.5 feet high, and was printed in about 1 hour. So you can basically print a good part of this bridge in a day, and then the rest is the post-tensioning of it. And again, the interesting thing is, as you can print, you also can incorporate what we know as some shear reinforcement, like textile reinforcement, and then you can include as well between the layers, and you can then do the post-tensioning. The interesting also in printing, you can change the profile of the post-tensioning location in the same section or in different sections. So this is an example of a bridge that is we laying out here the way to do this post-tensioning, or this 3D printed concrete bridge quickly with different segments, and having some special segment joints here designed to prevent water ingress into the bridge, and some of the post-tensioning to go inside the bridge. Again, this is some of the work we've done with a group of colleagues in Nebraska, showing that actually we could apply the same concept into 3D printed of using UHPC, 3D printed UHPC, where the bridge, the whole thing can be actually printed on site, then it could be post-tensioned and transported to actually have very quick restoration of a structure. The 3D printing process, as we all know, relate to actually starting by design of a cross-section like the cross-section you've seen, and slicing this cross-section using the G-code, then actually printing. And the printing can include the similar structures or sections like the one we showed, or could include also samples that you can be using for testing. We've done some work about trying to identify the factors that's affecting 3D printing of concrete. And of course, rheology and green strength of concrete is in the heart of this. So we developed this what we call as a tetrahedral-like model, similar to the silica model, where the 3 points in the base are basically the materials used, including binders, aggregate, and rheology modifiers and additives, the mixed design being used, and the printing process that is used. And this is all actually getting together to affect the rheology and the green strength of the material. Rheology basically its the ability to place this material into the layers required and in the geometry required. That's controlled by the viscosity, the yield strength, the structuration rate, the ability to build up, and the thixotropy. And then the green strength represented by the modulus of elasticity and the shear modulus of the green concrete that is still in the fresh state, and that all of those factors, along with the rheology, affect the hardened final properties of the concrete. In this model, basically, we show that as you are placing the concrete and the concrete is sheared here in the printer, you actually are, this shearing ability to shear this concrete is a function of the dynamic yield stress of the concrete. And to be able to build these multi-layers, the factors affecting this are the different factors of the printing process, including the contour length, including the vertical buildup speed or rate, including the speed also of the nozzle and its movement. And basically what happens during 3D printing is that the material change here from that composition first to actually as the materials start to harden, the thixotropy of the material builds, and then this material have enough strength and capacity to be able to resist the loads applied from the different layers on it. So a very critical one is known as the static yield stress. And that static yield stress is basically the representing the material ability to actually resist stress in the fresh state as you are printing the different layers. The whole discussion here is, of course, based on the material strength, not on stability, which we'll talk about it later. But basically, as you print the material and you do the extrusion at the time T sub 0, the material strength or the yield stress of it is growing, and the material change from the fluctuating, basically very fine powder, cement powder, to hardened material and the network of the interacting cement base. And as that happens, that actually the yield stress is growing. And what matters really is that at any moment that the yield strength of the material is higher than the tangential stress that is developed because of the gravity load of the top layers. You can see that the different stages here related to bumping and extrusion of the material, deposition, the development of the green strength, and then that rapid strength gain related to actually the material being able to have enough strength in it, shear strength in it, to resist the stresses. And that change from the time here to the time where the material has its full green strength is what we call the thixotropy of the material, which can be tested and or characterized from rheology testing. This is a simplified way of looking at the growth of the stress and the strength of the material. So this is the static yield stress again, and it is growing, assumed here to be growing linearly with time. And that is the increase in the stress, the tangential stress that is because of the built layers. And as long as the strength of the material, the green strength, is higher than the stress that is growing, then the material should be able to carry the different layers. And if we use this equation, we can rewrite it basically rather than at this intersection point to actually find what is the required thixotropy that is necessary to actually allow us to use this rate of construction of the material of the concrete on the top. So you can actually design for a specific thixotropy. So we did some testing on the concrete, on 3D printed concrete, standard mix of concrete to achieve the requirements for the rheology. We assessed the rheology of the concrete using the typical rheometers, and we measured the viscosity, the static yield strength, and the thixotropy of the material. And we also measured the slump and the setting time. We also measured the buildability by building or printing 1 and 2 and 3 filaments. One of the important things I missed to mention in this slide here, again, this only represents the strength of the material, does not represent the structural stability and the tendency for buckling, which we're going to talk about it later. So the filament strength here is being measured to actually quantify the ability of the material to allow buildability. And as you can see, as the filament number of filaments increase, the number of stacked layers can increase. And that is in the concrete mix we choose. Then we decided to actually examine what is the significance of the printing pattern, because you could change the printing pattern you are doing on the anisotropy of concrete. This is always a question that came by a lot of industrial partners that we've been trying to work with and trying to convince them with the large scale 3D printing. Does the concrete have the same properties? That's the question we have on the 3 direction, given the fact that you are printing it. So in the directions we are printing here, the X and the Y are the plane direction and the Z is the vertical direction up. And we examined the change of the directions between the 0 degree here, defined in this direction, the 90 degree, 45 degree, and minus 45 degree. So we printed the different directions and we quantified the concrete strength and the modulus. So in this properties, as we are looking, we are identifying a few variables. So basically, these are the filaments, these are the layers. The voids between the layers is in the interface between the layers is the interlayer interface, and the interface between the filaments is the interfilamentous interface. And using this, now we can quantify what is the effect of those interfaces on the concrete capacity. So we printed many concretes, as you can see, with some in the 0 in the X direction, and we actually tested the density. We tested the compressive strength, and you can see here the change in density. And we also tested the conventional cast concrete made of the same exact concrete we are 3D printing. And you can see that in almost all the directions, independent of the direction, the density of the 3D printed concrete is a little higher than the density of the conventional casts. And we measured the compressive strength of the concrete as well. So this is the increase in density. We measured the compressive strength, and we observed something interesting, that the compressive strength in the X and the Y direction is actually higher than the compressive strength in the Z direction. And all these observations, by the way, when we do them with multiple measurements, about 5 samples, and we do statistical variability testing to make sure that when we say it's lower, then it is statistically lower. We did the same on the strain at failure, and also interestingly on the modulus of elasticity, which is showing the exact same behavior. So this is again the X and the Y directions of this is a cut of the concrete we are printing, and this is the X and the Z direction. And you can see that here you can start observing the interfilamentous voids between them. And what we did to actually examine what is happening at the interface, we took concrete from both the interfilament interface location and the interlayer interface location, and we did a shear test. And this is the shear strength test of the interlayer interface, and this is the interfilamentous interface, and that's the conventional concrete. And interestingly, none of those failed at the interface. And the failures all was happening in the concrete, and actually the shear strength of all of them have been higher than the shear strength of the normal concrete in the just as cast in the conventional cast. So to examine this, we went and we took some sections and we looked at the voids, and we looked at the interlayer interface and the interfilamentous interface. And what we noticed that in the interfilamentous interface, there could be higher voids dimensions. They are not continuous, but there are voids that is higher in dimension than the micrometer ones that you typically see in the interlayer interface. So what we conclude of this is actually, in the case of 3D printed concrete, the increase in density and in compressive strength in the X and Y direction is related to the fact that during printing, the nozzle pressure compact the concrete, and therefore the concrete have a higher density, and therefore a higher modulus of elasticity and higher strength. In the Z direction, it is lower because of the preferential interfilamentous interface that could be actually and sometimes connected, that would get the material to be weaker in the z-axis. However, it's weaker, but it is still stronger than a similar concrete of the same, made of the same material, but not 3D printed. So there is anisotropy that is in the 3D printed concrete, but in all the directions, the concrete is stronger than the case of the non-3D printed of the same mix, assuming the mix is 3D printed. We also looked at 3D printed polymer concrete because we are interested in polymer concrete for its ability to provide a higher ductility, for its ability to improve the bond strength between the layers, and to limit a lot of the durability problems that we see in normal concrete. So we've developed over the past few years a few types of polymer concrete. Some of them are actually very interesting, that are nano-modified with nano-alumina nanoparticles and with carbon nanotubes particles. And this is an example of a tension test of this concrete. And you can see the significant improvement in the tensile strength and strain ductility. So the same strength almost, but the ductility is much higher. It's about 10 megapascal in strength, but significant improvement in ductility with the use of the alumina nanoparticles in the range between 0.5 to 1 and 2%. This is an example of one of these polymer concretes. We can see the level of ductility of the nano-modified polymer concrete. We use this test to actually, because usually in a concrete test, when you do a test like this, you get complete cracking of the concrete. So, but here you can see that the polymer concrete bended and actually the support failed before we are able to fail the concrete. And it's very high ductile material. We looked at the microstructure of this nano-modified polymer concrete, and we actually found significant changes that is happening in the reactivity of the polymer matrix itself that will allow this superior ductility, especially with using alumina nanoparticles that actually change the microstructure, the polymerization process in the polymer concrete. We also looked at using some carbon nanotubes, some carbon nanofibers to improve the conductivity of the polymer concrete. And here is a test similar to this test, but we did it in cyclic loading, where we use the carbon nanofibers to improve the conductivity. And we use the percolation level of about 2%. This is where the becomes very percolated, the polymer concrete, and can conduct current. So when with a source meter here, we basically are measuring the change in conductivity as we do cyclic loading. And what we decided as from the measurements, we actually can measure the change in the load displacement. We can infer the modulus of elasticity or the stiffness of the polymer concrete and the damage that's happening in it. That's the mechanical damage that's happening during the cyclic loading. And we decided to compare this to actually the electrical damage that is happening by the change in electrical resistivity in this polymer concrete. And this is very interesting because here, this is the change in electrical resistance and versus the number of cycles in thousands. This is the neat polymer concrete, where it actually does not, same polymer concrete mix with the made of epoxy concrete without any of the carbon nanofibers. And basically with the high range of change in stress we are doing, the specimens failed after 50,000 cycles. While the polymer concrete, nano-modified polymer concrete, you can see here the first the significant improvement in its conductivity, or change in its conductivity, significant improvement in the material that doesn't fail under a large number up to 300,000 cycles of load. And the interesting, this is the electrical change, which is very much matching the typical mechanical damage change we know, where it goes in the typical cycles for fatigue, the primary, secondary, and then tertiary up to failure. So with this, we could actually see that we can use the nanomaterials and the observation of the electrical conductivity to actually detect the damage that is happening in these materials. So we started using also the polymer concrete and some of the modified nanomaterials to 3D print it. And to do this, the only difference than the concrete case is that the case here, the matrix is a polymer. So in these polymer concretes, by the way, there is no cement. We are replacing the cement completely with a polymer. And here the change that is happening to develop the static yield stress is that cross-linking that happens in the polymer that result in the material being able to observe higher stresses. We evaluated both the rheology of a polymer and the rheology of the polymer concrete. And while the rheology of a polymer is a typical Newtonian relationship between the shear rate and shear stress, the polymer concrete follow what we call as a Bingham pseudoplastic model. And this is the measurements for the polymer, and you can see it is very linear, and that's the change in the viscosity of the polymer with time. This is the polymer matrix before we actually add the concrete aggregate to it. And these videos just show you the mixing of the polymer and the filler, then adding the aggregate to it, and then actually 3D printing of the polymer concrete layers. This is the 3D printed polymer concrete mix that is using Novolac epoxy for polymer concrete 3D printing. One of the issues of interest to us is that for using this in the industrial application scale, we really need to be able to predict how is going to be the behavior of the material, not only from the simple calculation I shared earlier, which is basically based on the thixotropy and the development of the stresses based on the layers, but also realizing the effect of this on the stability. So to do this, we have to handle this material like the soft material that is the green strength material, like we are modeling a structure. So to do this, we need to get the green strength of the material, which is the fresh polymer concrete ability to carry the load, and then look at the green strength and also the failure criteria of this, which we used here, the more column failure criteria. So to be able to, so basically testing this material like a soil, and finding the relationship between the normal strength and the shear stress in the material, and finding what is the cohesion and what's the friction angle. So to do this, we actually built the polymer concrete, and we did this test, as you can see on the top, where we are actually applying normal stress and we are applying a shear stress and measuring the stresses required with time. So you can see here we are repeating the stress with time from the time zero of the same polymer concrete mix. So every one of them is a different sample, of course. This is a time 0, this is a time 30, 60. And you can see that between 60 and 90, this is the material start to developing some of its shear strength, and again, much higher at 110. So this is that for a specific axial applied load, which is 12,000 PSI. And you can see here the relationship between the displacement and the shear stress. We repeated the same load for different loads. Here is for the case of 20.7 Newton. And you can see that the material here, this is at 0 time, 30 minutes, 60 minutes, 90, and 110. With a higher shear normal stress, the shear strength is higher. And we can actually use these relationships to find the relationship between the normal and the shear stress as the time passes, and the evolution basically of the failure envelope. And you can see that this is the cohesion of the material and how this is changing with time. So some main changes happening between the 60 and the 90 minutes, where the materials start actually developing because the polymerization builds up higher. The interesting thing, because this is a polymer concrete, we can actually control when this happens. We can control the process of polymerization to make it to happen a little earlier or to happen later, based on the construction process and our interest in it. But using these curves, we actually can see the changes in the cohesion, and we can see the changes in the friction angle as well. And with this, we build these models. This is for this specific mix we have, where we can actually predict the cohesion with time, and we can predict the change in the friction angle with time. Now we have this, we can actually build a finite element model, because our interest is to actually build and 3D print a polymer concrete tank for chemical applications. And with time, you can see that we can actually now, because we have these contours, we have the specifics of the material properties, we can actually simulate the process of 3D printing of the polymer concrete, and we can identify the stresses, and we know the strengths, so we can actually identify if there could be a failure. And there's other features we are adding to this model. But using a model like this, you can actually now move from the material strength development to actually a structural. So if there is issues related to buckling or collapse of the material, that we can discover prior to printing. So this is the 3D printed polymer concrete we are modeling here. And what we are doing now, I have a PhD student who's doing actually a great work in this. He's monitoring now the development here and trying to match it and so that we can validate our model. In the meantime, we are trying to actually address one of the big topics discussed by many of the speakers today related to CO2, and that, of course, was polymer concrete. That's also an issue. So what we are trying to do is actually we're developing a biopolymer that is polyurethane-based biopolymer, and we actually use this polyurethane polymer to mix concrete and develop concrete specimen. That's the stress strain of it. And you can see that we can develop a 4,000 PSI concrete. And the work we are doing today is actually taking this to be 3D printable, where this is definitely a much lower carbon footprint material than the typical material. Last part of my talk is related to composites and the value of using 3D printing in it. One of the big issues in fiber reinforced polymers that we all use since we started using it is the fact that it is linear elastic. The material is very strong, typically compared to what we typically need, but it is linear elastic, does not have any yield plateau, making the design usually challenging and requires a lot of issues or methods to address the ductility. So one of the thoughts we have is, can we use the 3D printing to actually make a ductile polymer concrete? I'm here differentiating between the materials being linear or having a ductile behavior or having pseudo-ductile or progressive failures. And we are using, in this case, the carbon fiber. So we have a patent that was done in quite long, some time ago, issued in 2019, but filed about 4 or 5 years ago. And in it, we just modeled how the shared stiffness concept can allow us to develop ductile, pseudo-ductile FRB. The interesting, at the time we developed this, or we filed it in 2015, we did not have the 3D printing technology. So we did not know how can we make what we are suggesting that can be made. But then later, we actually have the 3D printing technology where we can actually print the different layers of the FRB using thermoplastic polymers and filaments and using fiber spools. So using fiberglass and nylon thermoplastic matrix, we decided to try to show what we have been trying theoretically can be done with 3D printing. So this is an example just to show the 3D printing of reinforcement, an FRB reinforcement that we decided to actually make it to have a shape that is topologically optimized. With the interest to show that we can control the layers, we also can control the geometry of the FRB if we need. So the idea here is that when we are printing, rather than printing the FRB all at the same direction, we can actually change the different layers we are printing. So going from the orientation of the FRB here is going from 0 orientation to 90 degrees. So by changing the number of layers at each one of these and the angle of orientation, we can actually control the stiffness of the material. And we can, with the control of the stiffness of the material, we can achieve the concept of the shared stiffness we have been discussing earlier. So this is the tension test of the FRB that is 3D printed. And what we tested first is we tested first the layers of the 3D printed FRB without actually, so this is just the material at 0, 12, 24. So this is the angle we're talking with the vertical, and this is the behavior of the FRB printed material and the thermoplastic itself, the polymer matrix. At the different layers, we got the strength and the modulus of each one of them. And then we went to the finite element and we designed a behavior that would show some pseudo-ductility. And you can see this, the pseudo-ductility here will have, this is a different layer number, but this is the thickness of the different layers at the different angles. And with this, through our modeling, we showed that we can have some sort of progressive failure where the failure actually wouldn't happen suddenly and will have some ductility in it. So to achieve this, and again, the strength is not that high, but I just need you to keep in mind that we might be using today an FRB that is 2000 megapascal in strength or 1000 megapascal in strength, while our steel is 400. So if we can make a FRB that is ductile and it's 250 or 300 MPa in strength, that's definitely is more interesting in design as a ductile material than a 2000 MPa that is actually with no warning at failure. And that's our objective. So we tested this is the modeling, then we started to do testing. And as we started to do this thing, we started to examine also the significance of debonding some of the layers to allow it to work, because of course, the layers, when bond, its behavior is different than debonding. And we used fully debonded layers, and we also used partial debonding using thermal blocks during the 3D printing to prevent the debonding of the material. This is some design, and it shows the area of the layers, the number of layers used, the orientation of those layers. And our original patent was basically that the whole process is related to keeping and maintaining a specific coefficient of variation between those layers to maintain the ability of the shear stiffness. And this is the testing of it. So this is the fully bonded material. You see, it does not have any ductility, but actually you can start getting, and this is actually reaching 150, you can start getting some pseudo ductility here for the case of the fully bonded or the case of partially thermal block debonded. We changed the design and we actually got better results. This is for the case of the bonded, and this is for the case of the thermal block, and this is fully debonded. So we can get 200 megapascal glass fiber, and actually it is high ductility material with pseudo ductility and progressive failure. Of course, we're doing more work on this, and we are looking at the debonding and the failure patterns to learn how can we actually change the thermal blocks or the thermal debonding during the printing process to produce a ductile composite. The last thing is the same composite. We actually are also thinking of adding to it some computational capabilities. So this is by adding some flexible wiring and flexible controllers, where we actually can fabricate the composite. This is not 3D printed yet, and the composite will actually have its circuit for computations, for sensing, and for computation. And that's interesting. You can see that we actually coded this to actually start putting some light once a specific strain reaches in the composite. And the idea is that if that is possible, that you can do computations inside the composite or in the concrete, then you, in the future, you might be actually provide some feedback or some change in stiffness by using shear memory alloys in these composites to actually protect it in the future, combining both the monitoring and the computing and the feedback. So I'm not going to read all of this. Basically, we've been doing a bit of work on 3D print concrete, polymer concrete, and composites, trying to investigate those new innovative technologies and their use for resilient infrastructure. Some of our publications over the years on these, I'd like to thank all these companies that has been an agency, funding agencies, been funding our work continuously. I'd like to thank the team that does not get the chance to get the credit when I present. So they are here as well. We are the ones doing the work, and I'm open for any questions.
Thank you, Dr. Mahmoud, for this very good presentation. It goes from it covers everything about the 3D printing actually, and we learned a lot from it. We have a couple of questions here. We start with the first. It says that what are the companies involved in manufacturing the 3D printing of concrete, and what are the maximum size of aggregate used up to date?
Okay, for the companies involved, there's been a lot of companies we've been talking with and working with. Some of them are 3D printing concrete companies, and some are not 3D printed concrete companies. But let me answer the question related to, and you can see some of the logos of the companies in the presentation. Related to the aggregate size, we've been doing typically 5 millimeters. But you should be able to actually also design mixes up to 3/8 of an inch, 10 millimeter for 3D printing. So usually it's a smaller aggregate size.
So we are speaking about mortar size.
Yes.
Okay.
But I don't, let me just mention the issue of mortar, because I still would call it concrete because we call UHPC ultra high performance concrete as concrete, and it has a nominal maximum size of 160 micrometer.
Sure.
So
Yeah,
it is concrete. It's just the nominal maximum size. If we are interested in this type of materials, will be dropping. I think 3/8 of an inch is very possible. 10 millimeters.
Great. We have another question. Says, does the interlayer speed or deposition of printing layer impact the density and the strength of the 3D printed concrete?
Of course, it will impact, but basically the interest is, you should be designing the material to fit the printing speed that you of interest. So this is not, it's very difficult to think of 3D printed concrete as a concrete mix that would fit all the structures that is going to be one. So based on the contour length, the speed, also the height, the progressive of the height, all of these speeds, your concrete mix need to be designed to meet these. So yes, if it doesn't match, it will affect the material and you can end up with cold joints.
He's asking, is that affect the density and the strength of the concrete?
It wouldn't. It's the densities, no, it wouldn't. If it's designed correctly, and that is what the concrete you designed it for these variables, it would.
Okay. So this next one, how this may impact the properties in comparison to a regular concrete. This is a continuation of the same question.
Yeah.
So if you want to compare,
as I showed, we compared mechanical properties. Typically, it is stronger because of the pressure of the nozzle that is happening. The 3D printed concrete is a little stronger than the same mix made of the same material if it is cast in the standard way. So it's not going to be weaker. That is the bottom line. It's not a weaker material. It is pretty strong.
Back to the first presentation of today of Professor Julie, he was questioning about what is the largest 3D printer that exists now. Is that can be capable of like printing a whole nuclear power plant?
We've seen actually printers. We've seen companies. We discussed with them that actually printing houses today. So the ability to print large structures exists. Now, how are you going to print a 3D printed power plant? I would think the idea, some of it might be as we should as precast elements, but 3D printed precast elements, where you can actually speed up the process of precast and allow it to be done on site, for example, or large scale of it. I don't think I haven't seen the printer to do a full power plant one time yet. But I think it's not that difficult because of the robots and its abilities, as we've seen it in doing houses and doing large structures. I think it's going to be in the future.
I was in a visit like maybe last month for a precast factory, and they mentioned that the main issue with them is the forming, to assemble the form and put the steery bar and deassemble the form after they cast. This is the most time-consuming process for them, and they are thinking about shifting to the 3D printing inside the precast factories. It will save a lot of money for them.
And one of our supporters, Castillo Priestres, is actually, we're discussing that with them, and that's why they are supporting us, because the idea now reinforcement is going to be different things. So the use of fibers, the use of post-tensioning. And there is a group of methods to use reinforcement, and we've been discussing it in ACI 544. There is many solutions. None of it is final yet, but there is a lot of solutions where you actually, especially now when we are discussing 3D printed UHPC, the need for the reinforcement is much limited. We've also used reinforcement like the fiber, the different layers of fibers in between the printing layers. As textile reinforcement to reinforce the 3D printed concrete, and it's been very successful.
Another question coming says that what are the materials used for producing FRP composites?
It was glass fiber and nylon as the matrix, but there is a big family of materials of thermoplastic, because most of them are thermoplastic polymers that is in 3D printing. We've been using ABS, we've been using TPU, we've been using a lot of other polymers, along with glass and carbon fibers. Both are available.
Okay. I think this all the question. So with this one, I thank you again. Thank you so much, Dr. Mahmoud. Thank you.
Thank you.